Before we had rockets, the only way we could think of to get into space was to shoot people out of giant cannons, which is a pretty ludicrous idea, of course. So today we will be looking at, oh right, shooting people out of giant cannons. Our topic today is probably the most conceptually simple of all the launch assist systems we will look at, but at the same time has a lot of engineering difficulties, many of which we will skim over for complexity. It is also a device with many names: mass driver, space gun, electromagnetic catapult, railgun, coil gun, Vern gun, and more. Unsurprisingly, I prefer space gun since there are no R's in that, and me pronouncing railgun tends to sum up the image of us shooting a whale out of a giant cannon. However, in each case the basic concept is the same. You are accelerating a projectile down a long barrel for it to exit out the muzzle at very high speeds. For space travel, this has the advantage of letting us get something up to high speeds without needing a rocket or an onboard power system, except for some maneuvering once you are clear of the cannon. They also typically use electromagnets to provide the push instead of gunpowder. This lets you provide an even and constant acceleration the whole way, which is necessary since human bodies can't withstand the kind of forces inside your typical gun, and neither can most electronic or mechanical devices. Those can usually be built to better handle such acceleration than a human can, permitting a shorter tube, but still a very long one compared to anything we think of as a gun. The notion is to have a very long track inside a tube evacuated of air, so you can accelerate a passenger or cargo pod down it, picking up speed without air interfering in that. In many ways, a space gun is no different than a vacuum train either, such as the proposed Hyperloop. One of the big things working against vacuum trains like the Hyperloop is the sheer expense of making an airtight tunnel hundreds of kilometers long, and the same is true of a mass driver, except we need to lift the end high up where the air is much thinner, the higher the better. While the physics of electromagnetically propelling a pod down a vacuum tunnel are quite solid, the actual engineering is much harder. Let's discuss the basic physics next. Whenever we discuss objects accelerating down a long track, we have a simple relationship between your final speed and your acceleration and the length of the track. If the object is undergoing uniform acceleration from rest, and isn't subject to air resistance at least. Your final velocity is the square root of twice the acceleration times distance. Your velocity rises with the square root of either acceleration or distance. If you want to double your final velocity, you need the acceleration to quadruple or the track to be 4 times longer. We want a nice constant acceleration at the highest rate we can produce that people or cargo can handle, because it makes for a shorter track. Let us consider getting to orbital speed, 7,800 meters per second. If we accelerated at 10 meters per second squared, just a hair over 1 g, our track would need to be about 3,000 kilometers or 2,000 miles long to achieve that speed. You'd spend about 13 minutes slamming through that. If you wanted to exit near New York City, your track would need to start in the Rocky Mountains. However, if you already saw the Skyhooks episode, you'd remember we could use one of those to take something into orbit if it could link up with the Skyhook at about half the normal speed, which would require only 1/4 of the track length. That's still quite long, but it means your track exiting at NYC would only need to start somewhere in my own home state of Ohio. The same track could achieve full orbital speed at 4 Gs of acceleration instead of just 1. That's an uncomfortably high acceleration, especially without a G-suit like a fighter pilot wears, but comparable to what crews experience during rocket launches. Now for a fixed final speed, 7,800 meters per second in this case, track length and acceleration are inversely related. Double one, half the other. Double your acceleration, half your track length, same final speed. Quadruple one, cut the other down to 1/4. If we accelerated down a track at 4 Gs that was meant to link to a skyhook at half normal speed, our track would be about 200 kilometers long, or 1/16 our original track length, designed to get a spaceship to full orbital speed at just 1 G of acceleration. This is not an episode on skyhooks, we already did that, but you can see why I like the notion of using them in tandem with this method. It saves you a lot of expensive track. Of course, you can cut that track down even more with higher accelerations, but there are limits to what a human can handle. This is also true of cargo, though we can get away with shorter tracks and higher accelerations for most cargo. Bullets, for instance, undergo thousands of Gs of acceleration in a gun barrel. Your typical bullet emerges at a few times the speed of sound after traveling down a barrel less than a meter long. And 100,000 Gs is not unusual for an acceleration rate. More than 1,000 times the acceleration rate that would turn a person into chunky salsa. To reach orbital velocity, such an acceleration would need a barrel just 300 meters long. There's no advantage to that level of acceleration in this case anyway, at least on Earth, because we want a tube long enough to stretch up high in the atmosphere where drag is low, mountain peak high at least, and we'd rather it emerged a lot higher up, where the air is much thinner, and we don't want our projectile emerging straight up either. We want a track that is longer than it is tall, so that your velocity is mostly horizontal, not vertical, as that is what is needed for an orbit, and is the reason why rockets roll over on their sides after they get up a ways. We don't want to try to build up speed in the thick air or exit in that, so we need it to emerge where the air is a lot thinner. The track does not have to be a straight line either, but bending and changing directions entails its own problems. If you try to turn at those kinds of speeds, you will undergo a lot of centrifugal force, which would just add to the acceleration we are trying to keep to a minimum. At orbital speeds, you can easily need a turning radius of 1,000 kilometers or more to avoid crushing yourself under the centrifugal force. So you can't just run the track along the ground, pivot sharply upwards on some mountain or tower, then do it again at the top to get yourself horizontal again. This is also why we can't loop a ship around over and over on a circular track to build up speed first. Only the orbital rings we will discuss near the end of the series allow you to run around in circles building up speed on that scale without being crushed by centrifugal force while turning, and it has the specific advantage of letting you do it upside down so that the gravity is subtracting rather than adding to the force you will feel while turning. But you do want to be as high up as you can be while exiting, which is where a lot of the engineering problems and expense arise. The reason for having the tube exit up high is to get the thing being shot out of it above the atmosphere and all the friction and drag it will produce. By the time you are 50 kilometers up, the density of air has dropped to just 1,000th of normal, and it's down to less than a millionth by the time you get to 100 kilometers. Trying to get anything up that high and stationary is nigh impossible, and the tubes will have a lot of weight just from their own structure, not to mention magnets, power lines, and vacuum pumps working to make it stay as close to vacuum as you can reasonably get, though that last gets easier as the air thins out with altitude. But as thin as the air is up top, it will still fall down the muzzle fairly quickly if you don't have a way to stop it. Now you could just have a door at the end that slid open when the projectile was about to come out. This hardly requires some sturdy hatch akin to a bank vault door that we usually picture for an airlock. The pressure differential is quite low, so that there's very little force acting on this hatch, and anything airtight will do the trick, even a thick sheet of plastic might suffice. You still would not want to run into that going at Mach 15, but it's not hard to include some automatic safety device that would blow the muzzle cover free if the normal opening mechanism failed. However, we do have an option on the table that's fairly high-tech and reminiscent of the force fields we often see in shuttle bays on spaceships in sci-fi. This is the plasma window. A plasma window is essentially a window where we use plasma instead of glass. We can confine a plasma inside a magnetic field to create a flat plane inside a cylinder, and at high temperatures it interacts with the air touching it in a way similar to how oil interacts with water, not letting it pass through. This appears to work not just at low pressures, but also at ones up to 9 times higher than standard air pressure, so this technology might be handy on places like Venus or Jupiter too, where the atmosphere is a lot denser. It's not necessary for our Earth-based mass driver, but it's pretty neat, and obviously has more uses than just as a muzzle cover for giant guns. Of course, it also uses a fair amount of power, as does the entire giant space cannon, so we should talk about that next. Now, it is being supplied power from the ground, so nothing high-tech is really needed on the power generation side of things, My own preference would be for an atomic source, but anything works so long as you have enough juice. For a 10-ton capsule doing 4 Gs of acceleration, your peak power consumption will be a few gigawatts. That's a lot of juice, comparable to the Hoover Dam, but certainly doable, especially since it's only briefly, so you can use capacitors and batteries, or just give it its own dedicated fission reactor or solar panel farm. Transmitting that power is a bit harder, since you also need very high voltage lines stretching the whole length in order to get power to the magnets all along the tube, all of which is adding weight to your tube, which is already pretty heavy, and which we need to find a way to suspend at altitudes not only taller than any building we've ever made, but any mountain too. This represents quite an engineering problem since the barrel stretches many kilometers off the ground, and weight is a big issue, so is wind too. With a space elevator, we were always talking about a cord that was fairly thin and dense. There isn't that much force acting on it even during a hurricane, compared to the other forces in play of tension and weight. Here though, we are talking about a tube a few meters or more wide that is hollow, so not much weight resisting that air, though it can get lighter as it gets higher, since the tube need not be as sturdy as the outside pressure drops, and wind force will drop as you get higher too. So you have to have some way to hold that up in the air, and also preferably help you resist wind. We do have a ton of options on that score, many of which will be getting whole episodes themselves down the road. The first and most obvious is giant pylons spaced as needed to keep the tube up, wider at the bottom than the top for reasons we discussed in space elevators. This is a pretty mass-intensive approach. Skyscrapers are incredibly expensive, and these would be far taller. But it is physically possible, and you are building a tower, not a skyscraper, which is way cheaper. The KVLY TV mast in North Dakota, built in 1963, remains the tallest structure in the Western Hemisphere, and was the tallest in the world until the Burj Khalifa overtook it in 2010. But while the latter took billions of dollars and years to build in the 21st century, the former cost only $500,000 and was constructed in just a month, a half-century earlier and lower tech. We could go a lot higher nowadays, with modern materials and higher budgets, so don't dismiss the idea of using this more classic approach out of hand. But we have 2 other approaches I want to mention briefly, though we will be saving a detailed explanation for later in the series. One of those is simply balloons, though this could take the form of balloons that the tube was suspended from, or essentially towers that were themselves made to be buoyant, and we've gotten balloons as high as 50 kilometers. Of course it will be less if it is being used to hold up weight, but even then that is probably tall enough for a space gun, since air is orders of magnitude thinner there than on the ground. And so while you still have significant aerodynamics in play, it does allow you to exit with much higher speeds without being subject to overwhelming air forces. This makes this a decent option if you are not trying to get the projectile to orbital speeds, but just skyhooking speeds. Needless to say, trying to hold structures up with balloons has a lot of issues you have to deal with, and so it will get its own episode. But we also have the option of active support, which I've mentioned before. We will explain that in detail in the upcoming Space Towers episode, but for now I'll just give the quick reminder that it is where you levitate a platform or hold a tower aloft by firing objects up it. In a way, it is the opposite of a mass driver, since you would have a smaller one on the ground shooting fast-charged particles up a tube, which is electromagnetically slowing them down instead of speeding them up, and the momentum the tube gains upwards is what holds it aloft. Shut that stream down and the tube drops, hence the term active support, though don't go assuming that would mean it crashed to the ground with tremendous force. You are talking about the same hollow tube we are accelerating pods in, only thinner, and we will see that's fairly safe in a few minutes. First, let's look at using it away from Earth. This series focuses mostly on getting off of Earth, so that's where we spent most of our time today. But as in other episodes, I want to take a couple minutes to discuss using this technology off of Earth. On airless places, moons and asteroids, it's a very good way to ship bulk metals out. We could have large metal production plants on the moon that were shipped back to Earth orbit potentially much cheaper than bringing it up from Earth. And it's also a good place to launch expeditions from, since there's very little gravity and no air cutting into your initial fuel needs. It's also way cheaper to build the setup there. The moon and other such places have much lower gravity, so building the trusses up to raise the gun is much easier, but also now not necessary. We lift the gun to get it over the atmosphere so there isn't any friction and drag on the ship or projectile, but most places with low gravity have no atmosphere to speak of. On Saturn's moon Titan, though, that is not the case. The gravity is a good deal weaker, 14% of Earth's, with an escape velocity of just 2,600 meters per second, just 23% of Earth's. Alternatively, the atmosphere is a good deal thicker than our own, so Titan is an ideal place for Earth-style devices, being easier to build from the lower gravity, as is arguably Venus, and amusingly the two share an abundance of nitrogen, something that is not too plentiful elsewhere in the solar system, but is vital to construction of extraterrestrial living spaces, be that terraforming places like Mars, or building habitats on moons and asteroids, or free-floating rotating habitats in space. So I could easily see a major export business on both Venus and Titan revolving around space guns firing huge, thin-walled vessels full of pressurized nitrogen gas to be used elsewhere in the solar system. And considering the quantities needed for any big project, the gun analogy is rather appropriate, since it would probably be lobbing those pods out at a rate similar to a machine gun. On airless moons or asteroids, these work great, no air friction, and no need for strong tunnel siding for keeping a vacuum. It's just a train track across the surface providing power and something to push against until your speed is high enough you can let go and zip off into orbit. However, on a place like Venus, where we do have a thick atmosphere, and when it is the atmosphere we are mostly interested in mining anyway, we can consider placing the entire space gun on balloons and floating it in the upper atmosphere. We will look at that option, balloons, more in a future episode. Now, buoyancy doesn't work too well in gas giants. They are mostly composed of hydrogen and helium, the same gases we use to lift blimps in the first place. But flight still works. And one problem with space guns not fixed to the ground is that they have recoil that is going to push them backwards. Now, the major reason to mine a gas giant is if you have a fusion economy. Quite a large one too, since while fusion uses hydrogen, it uses so little of it that a small canister of hydrogen gets you about the same energy as an oil tanker contains. Hydrogen has many other uses. It is necessary for making water or ammonia, for instance, but both of those are abundant in icy bodies in the outer solar system, and you don't have to fight a huge gravity well to retrieve them. So you probably only start mining gas giants for hydrogen when you have energy needs millions of times greater than we have now. If you do have such a fusion economy though, you can use the gas in the atmosphere to power your space gun and let it shoot pods of compressed hydrogen away as its own propellant to keep it moving. So you could easily see huge versions of these with large wings firing out compressed gas into space as its jet thrust to stay aloft. Lastly, they are good in orbit around any place, though especially where solar power is abundant, for launching ships out of gravity wells. Used in combination with skyhooks or space elevators we discussed elsewhere in the series, an orbiting mass driver need not be much more than a tether supplying power and something to push against, to let ships go flying off into the solar system at good speed. A mass driver does not need to be a rigid object either. It might just be a line carrying electric current with a magnet at one end to let it grab an incoming ship, which then decelerates using that line again as a source of power and to push against. Sort of like falling next to a rope and grabbing hold of it to slow down, like a zip line, only using magnets instead of your boots and gloves to slow you down. The same trick can work by having a cannon in space that shoots the tether out for a ship to run along, then reels it back in when it is done, letting you deploy at any angle on short notice and without leaving something to clutter up space. We mostly think of using these for getting higher speeds, but they can be used to slow objects too, much as a skyhook could be used to generate electricity instead of employing it to regenerate its momentum, or can be used to slow objects down for slow entry into an atmosphere. I should also note that you don't have to use electromagnetism to run these, but it appears the best option for most circumstances we'd use. A highly reflective backside to a pod could let you bounce lasers or microwaves back and forth, accelerating one much like we saw in the episode Interstellar Highways. And there are some cases where a light gas gun approach might be appropriate too. You use whatever is cheapest and safest that gets the job done, and that appears to be electromagnetic propulsion. We should discuss safety at this point. As the gun name implies, this sort of technology is obviously weaponizable, but a space gun isn't something with much safety risks in that regard. one built for getting things into orbit can't exactly be hijacked for shooting cities with, and repurposing one to deliver giant artillery shells, while certainly possible, is a pretty time-intensive and illogical process. There are far easier ways to get bombs wherever you want them. They are subject to accident or terrorist attack, like any of the other systems we've discussed, but as we've noted before, one can include parachutes and explosive charges to cause damaged segments to slowly fall to the ground. They are likely to be heavier than space elevators or skyhooks though, and wouldn't have any sections burning up on re-entry, so if they landed without being slowed down, they'd cause some damage right below, much like a falling bridge. So it is a good idea to build the length of it over mostly unpopulated areas. Since shorter versions generally end on mountaintops, and you can also build one in the ocean, this isn't too big of a concern. We also aren't talking about the whole tube coming down either, just the section between two towers or balloons. You would always build one of these things with detachable segments that you could blow free with explosive bolts. The same applies to towers if you are holding it aloft that way. You want to be able to break it into smaller chunks and let those fall a bit sideways so you can let the parachute slow them down, though big hollow tubes or thin towers aren't exactly going to hit with devastating speed and mass even without those. Again, you wouldn't want these near densely populated areas though. But the departure station can be in cities, since that is still on the ground and the launch shouldn't be either noisy or dangerous. So like the space elevators, this does allow direct launch from populated areas, making getting into space somewhat akin to an extended subway or train ride. A damaged tunnel isn't as bad as some have implied for things like the Hyperloop, and the same reason applies here. A small hole in the tube does not result in explosive transfers of air, as we discussed in last week's episode, Life Support. This is an even smaller issue at high altitude, where air pressure is just a tiny fraction of what it is on the ground. Blowing a hole behind the pod won't do anything, since the air won't catch up to the pod in time to cause problems, and if one is made ahead of it, it needs to be a large one to let enough air in fast enough to cause major problems, and in such cases, you just jettison the damaged section, and as much as is needed to give the pod enough space to dodge the upcoming section so it can then glide to the ground. Also, the places where the leaks come in fastest, near the ground where pressure is higher, are the places where the leaks matter the least. The first few kilometers of track don't involve particularly huge speeds yet, so you aren't that much impeded by a slow leak there. Now on the cost side of things, one of these can get fairly pricey. The estimated price for the Hyperloop is about $6 billion, and we also have to elevate ours. Estimating the price for that is pretty hard, and also depends a lot on how we are doing it. But the estimated price tag for the Hyperloop would represent your absolute bottom figure, excluding the much shorter and lower altitude version meant for high acceleration of cargo pods. The best known mass driver design is called Stow Tram, and they did put together a pretty solid proposal with costs, so we will look at those. Stow Tram's Generation 1 version had a price tag estimate of $19 billion. And that version was designed for unmanned pods to be fired down a 130 km long tunnel at 30 Gs and exit from a mountain peak. Their Generation 2 design, a 1,000 km long tube that would exit at 22 km altitude and handle passengers at 3 Gs of acceleration, had a price tag estimate of $67 billion. Both versions get their payload into space for a bit over $100 per kilogram, a small fraction of current launch costs, though still more than a space elevator. They also had a Generation 1.5 design meant for a lower exit speed to be used in tandem with a skyhook, and that would have a much shorter track length than the Generation 2 design of only about 270 kilometers, and again exit from a mountain or higher. I am particularly fond of variations on the Generation 1.5 design of Stow Tram. A space gun of this variety would shoot a hypersonic plane out of them at the highest speed and altitude you could practically make, then link it up with the best skyhook you can make. It becomes a 3-step process that represents the best means for getting tons of cargo into orbit for a low price that we could also build today if we had to. It would have much lower launch cost per kilogram than the traditional rocket. Of course, we are no longer focused on traditional rockets anyway, and the next episode in the series we'll be looking at reusable rockets instead. The schedule for the series after that remains tentative, but should go to balloons and buoyant structures next, then space towers, then launch loops, and finally to orbital rings. Next week, however, we will be returning to the Alien Civilization series for Dead Aliens, where we will discuss the notion of extinct civilizations, and start wrapping that series up for a return to the Fermi Paradox. For reminders when those episodes come out, make sure to subscribe to the channel. If you enjoyed the episode, don't forget to hit the like button and share it with others. Until next time, thanks for watching, and have a great week. Thank you.